Many engineering systems are designed to operate under changing conditions, but what happens when an input suddenly jumps from one value to another? The answer reveals important information about system speed, stability, and performance. This behavior is captured by a concept known as the step response. In real engineering systems, signals often change abruptly rather than gradually. A transmitter may suddenly turn on, a voltage source may be connected to a circuit, or a communication system may begin transmitting data instantly. These sudden changes force the system to react and adapt to new operating conditions. Understanding only the steady-state behavior of a system is not enough. Engineers must also know how long it takes for the system to respond, whether it overshoots its target, and whether it eventually settles into a stable condition. These characteristics directly affect system performance. The challenge is finding a simple and practical way to observe how a system reacts to a sudden input change. This leads to the concept of the step response, one of the most widely used tools in system analysis. The step response is the output of a system when the input is a step signal. A step signal changes suddenly from one constant value to another, typically from 0 to 1, and then remains at that level indefinitely. It represents a sudden and permanent change in input conditions. Unlike the impulse response, which examines how a system reacts to an instantaneous event, the step response shows how the system behaves over an extended period after a sudden transition. This makes it particularly useful for studying transient and steady-state behavior. The step response provides valuable information about rise time, settling time, overshoot, and stability. These characteristics help engineers evaluate how quickly and accurately a system reacts to changing inputs. Intuitively, a step response can be compared to turning on a light switch. When the switch is activated, the room does not gradually decide whether to become illuminated. Instead, the system immediately begins responding to the new input condition. The way that response develops over time reveals the behavior of the underlying system. Physically, consider an RC circuit connected to a battery. When the switch closes, the capacitor does not instantly charge to the battery voltage. Instead, the voltage rises gradually according to the circuit's time constant. This charging curve is a classic example of a step response. Mathematically, the step response describes how the output evolves after a step input is applied. The shape of the response depends on the system's parameters and reveals important dynamic properties that cannot be observed from steady-state measurements alone. Step responses are widely used in RF and communication engineering to evaluate how circuits react to sudden signal changes. Amplifiers, filters, and receivers often experience abrupt transitions during startup, switching events, or digital signal processing operations. In practical RF systems, engineers analyze step responses to understand bandwidth limitations and transient behavior. A filter with limited bandwidth, for example, cannot respond instantly to a step input. Its output rises gradually, reflecting the physical limitations of the system. At the system level, step response analysis helps engineers optimize signal integrity, reduce distortion, and improve performance. It provides valuable insight into how communication systems behave when operating conditions change rapidly. Although step response analysis is extremely useful, it does not provide a complete picture of every aspect of system behavior. Different systems may produce similar step responses while exhibiting different responses to other types of input signals. A common mistake is focusing only on the final output value and ignoring transient behavior. In many RF and communication systems, rise time, ringing, overshoot, and settling time can significantly affect performance even when the final output appears correct. The study of step response naturally connects to impulse response and system characterization. Since impulse and step responses are mathematically related, understanding both concepts provides a deeper understanding of linear system behavior and prepares engineers for convolution and frequency domain analysis. In this lesson, we learned that the step response describes how a system reacts when its input suddenly changes and remains at a new level. We also saw how step responses reveal important characteristics such as rise time, settling time, and overall system dynamics. In the next lesson, we will explore system behavior and examine how different systems respond to signals under various operating conditions. If you found this useful, like the video, subscribe, and follow for the next lesson.